All right, so this is my PowerPoint that has my announcement slides on it, and we're on the last slide, which means it's our last lecture together. Let's get started. Okay, so a couple quick announcements. Number one, homework 8 is due right now. So if you haven't submitted it, please do so up here. The solution is posted right now. Oh, by the way, I have your homework 7 graded. I should have put that up here on the announcement slide. Let me start passing that around. For the most part, everybody did pretty well. I don't really think there's too many major comments. Commissioner. Mr. Minnock is not here yet. Mr. Scott. Okay. So homework 7's graded. The solution's posted on Blackboard. I've given you those back. Again, homework 8 is due today. No late submissions because I've got the solution posted right now. The only other announcement I think is worth mentioning is the course evals. I have looked on there, and the only thing I know is how many of you have done it. Out of 14 students, only 10 of you have done it, not only, but 4 of you still haven't done your course evals. And so I'm guessing if you haven't done that, you haven't done the CLO survey on Blackboard. If you do the CLO survey, that's free bonus homework points. So if you haven't done it, the course eval and whatnot closes tomorrow at midnight. So if you haven't done that, I would. Like I said, it's free points. And you can say I'm the worst professor ever. Just please do the survey. Okay, sound good? So last topic is our exam review. So let's just get right into it. Okay. Let's see. The only thing worth mentioning that's a little different about the format of the exam is that instead of there being one set of conceptual questions and 3 problems, there's 4 problems. Okay? It's just because there's more topics on this exam. Bless you. A little bit about the format. So the exam will be closed book, closed notes, calculator, and a formula sheet. You can put whatever you want on the formula sheet except for worked out examples. I say that a straight edge will help with shear and moment diagrams, but I don't really know if it's shear and moment diagrams, just a straight edge would help. Also, since we're talking about Mohr circle, it's probably not the worst idea to mention. You had the little guide you had? Oh, you don't have it with you? But if you have some thing that can draw circles, like you can take the top off of that, or something to draw circles, probably not the worst idea in the world. I'm not going to say you have to draw a Mohr circle, but you may need to. So just worth mentioning. Now, you know my deal. We're going to try and be on time. We'll start the exam at 8 a.m. sharp, but if everybody that is supposed to be here is here at 8 a.m. or before 8 a.m., we will start early. So it's just on you. I'll have scratch paper, I'll have staplers. Any of the necessary section properties and any necessary simple deflection formulas will be provided. Unless I make you derive something, then I'm not going to just give you the answer. But again, you know how I go about things. As for coverage, this is going to cover lecture notes 9 through 12 on Blackboard and homework 6 through 8. So that's the coverage of the exam. Now, as for topics on the exam, we've got deflection. So make sure that you can write moment functions for very simple loading conditions. For those of you that are also in structural analysis, what I'll say is this is not structural analysis. So the moment functions and the analysis that we do in this course is a little easier than what we do in 312. So just worth mentioning. But you still need to be able to write basic moment functions for simple loading conditions. Make sure that you can integrate it twice. that you can solve for your unknown constants of integration using, boundary conditions. If it's fixed, that the deflection and the slope equals zero. If it's simply supported, that just the deflection equals zero. And make sure that you can determine maximum slopes and deflection. So, for instance, if you're trying to find maximum deflection, take the derivative, set it equal to zero, solve for x, plug that x into the slope or to the deflection equation to get your max deflection, and what have you. And that's the double integration method. The other method that we used in class was the method of superposition, which is basically using those previously derived formulas. Just as long as you can plug and chug, basically, you're good. The only other thing I think worth mentioning is your unit conversion for US units. So for deflection, remember, based on our unit system that we utilize, the conversion factor is 1728. For slopes, it's 144 to turn it into radians, but it's you throw an additional 180 over pi in there to throw it in or to turn it into degrees. All right, let's talk about stress analysis. So first up, based on a given stress state, can you determine another stress state at a different orientation? And so that's what's in that first box there. If you have a given angle theta, you can determine from an x-y coordinate system to a 1-2 coordinate system. Make sure that you can determine principal stresses and principal orientation. So remember, the principal orientation is at which there is no shear stress. So you can determine your principal angle, sigma or thetas at P, and then sigma 1 and 2 Roman numerals are your principal stresses. Also, when it's talking about Mohr circle, make sure that you can determine the center and the radius of Mohr circles. So the center is sigma average, and the radius is just what you see here. And then I want you to be able to interpret critical data from the plot. So what is sigma 1, sigma 2? What is your maximum shear stress? Remember the maximum shear stress. What is the maximum shear stress? Remember that?
The radius.
The radius. So, and just things like that. And remember your angle is 2 theta, because remember in the derivation, 2 thetas pop up all over the place. Combined loading, make sure that you can determine stresses from multiple types of loadings. I think that's a typo there. I meant to say determine stresses from multiple type of loadings. But basically what I'm saying is if you have a bar that's being yanked on, what's the stress? If you have an element that's being twisted, what's the stress? If you have an element that's being bent, what's the stress? I've said this before, that my goal is not to create a comprehensive exam. We've already had a test on axial loads and torsions. I'm not trying to test you, for instance, on that stuff again. But the nature of this course and the nature of these topics, some of the material bleeds over from one exam to another. So just be aware of that. If you have to compute stresses from axial loads or whatnot, it will be simple. That part won't be super complicated like it was on exam 1. Thin-walled pressure vessels, make sure you can determine, your stresses due to internal pressure, and elastic buckling. Make sure that you can determine buckling loads for columns. You've got your K values, determine buckling load, buckling stresses. Make sure you know what a radius of gyration is. You have the square root of I over A, and what have you. And that is exam 3. So that's it in a nutshell. So with that, I'm going to shut up, or at least shut up when it comes to my lecture, and let you all ask whatever questions you want about exam 3. So take it away. The floor is yours.
Can you do the last problem from
Homework
homework 7?
7? I don't really remember it.
It's thin wall pressure vessel.
Okay, hold on. Well, first off, I'm happy to do that, but that might take a little bit. Are there any other quicker questions I can answer? Is that something everybody wants to see? Okay, all right. Anybody have their book on them? Okay. All right. So we have the radius. So we have a radius of 125 millimeters and a thickness of 6.5 millimeters. Okay? So let's see if remind me, does the radius go to the inner diameter or to the outer diameter for a thin wall pressure vessel? Uh-huh. We had an example on this. Hold on. Hold on.
Oh, no, I'm thinking about more for the eye, just.
Hold on.
Is it the inner?
Well, I'm asking you. Everybody's like, is it the inner? No. Have some, tell me it's the inner.
It's the inner?
It's the inner. Okay. All right. Remember the inner. There we go. So, therefore, there we go. Therefore, the inner diameter is 250 millimeters, and the outer diameter is the inner diameter plus 2 times the thickness, which is what? 263. Do I have a second on that? All right. So, therefore, the area of the cylinder is pi over 4 times d naught squared minus d inner squared. And so what does that come out to be? Making y'all do some work.
$5237.82.
Do I have a second on that? And what are the units?
Millimeter squared.
Okay. Now, we got a torsion on here, so we're going to need a J, right? So what's J? Remember how to compute that?
Pi over 32.
There we go. Times,
D outer squared minus D inner squared.
oh, D naught to the 4th.
Oh yeah, I'm looking right at it too.
So what do we got for this? It's going to be big, because you're taking the diameter and you're raising it to the 4th. It's okay that it's big. Let's leave it big. I'll go ahead and tell you why. Does anybody remember if you take a kilonewton and divide it by a millimeter squared, what you get? A gigapascal.
$862 times 10 to the 5th.
Say it again.
862 times 10 to the 5th.
So 862,000. Oh wait, 862 times 10 to the 5th. Millimeters to the 4th?
Yeah.
Alright, close enough, Because I'm not going to worry about decimals and whatnot, we're just doing conceptual stuff here. Okay. Alright, sound good? Alright, so let's handle each load one at a time. Let's take the axial load. Okay, so the axial load, we have a sigma axial, which is P over A. So that's 5237.82 millimeters squared under what? What's P?
7.25 megapascal.
No. That's the internal pressure. What's the problem asking for? So it's asking for P. It's actually asking for P. So P is in doubt. Right? Okay. All right. So P is in doubt. All right. So sigma axial is P over 5237.82 millimeters squared. Okay. So that is a formula in and of itself, right? So is there a part A, part B, or what's the deal? What are we looking? Are we doing both parts, or?
I mean, just this one is fine.
Okay. All right, torsion. All right, we know that tau due to torsion is TR over J, right? Okay, now are we given a torque?
850 Newton meters.
Okay, so we have a torque that's 850 Newton meters. Does anybody remember how many kilonewton millimeters that is? So, for instance, our torque is 850 Newton meters. How many kilonewton millimeters is that? 850, yeah. So I'm going to take 850 okay, we're going to divide it by J, so 862 times 10 to the 5th millimeters to the 4th. Now, R, okay, now here's what I'm going to do with R, okay? If you take a torsional shaft and twist it, where are the largest stresses? The very, very outer edge. So how far is it from the center to the very, very outer edge? Is it
125 plus.
So what were you going to say?
I was gonna say diameter.
You're exactly right. It's half the outer diameter. So what did you say?
The outer radius, 125 plus 6.5.
There you go. There you go. So what I'll do, the way I'll do this here is I'll say 1/2 of 263. But we're all basically saying the same thing. Okay, what does this come out to be? Excuse me.
1.3 times 10 to the negative third.
And that's gigapascals. Multiply that by 1,000.
1.3.
Megapascals. Everybody okay with that? Now let's take the pressure. We have a sigma 1, that's PR over T. So that's, now the pressure is 7.25 megapascals. We have an R, that's 125 millimeters. And then this is 6.5 millimeters. And so what does that come out to be? $139.42. 139.42 megapascals. And what's sigma 2? It's sigma 1 over 2, which is what? Anybody remember that?
69.7.
Okay. Okay. All right. Now, before we go any further, can I see the book? Solve for P such that what?
For
What-
allowable stress.
The allowable tensile stress in the wall of the cylinder is 160 megapascals. Okay. Okay. All right. That's going to be the hard one, actually. So, okay. Okay, so we need to look at our state of stress on this problem. Okay, so here's the vessel, right? And the vessel is being yanked on by some load P, being twisted on by some torque T, and it's seeing some internal pressure, right? Now remember, if you have a stress block inside the pressure vessel like that, we have stress going this way and stress going this way, right? Remember that? All right. And then, here I'm going to pull up my lecture notes because I want to show you something. Find it. Hold on. Remember, here's your stress block, right? And so sigma 1 goes this way, sigma 2 goes this way, right? Okay. All right, so this is sigma 1, and that's sigma 2, and that's sigma 2. Is everybody okay with that? All right, so for this given problem, if we want to keep this simple and we'll say this is the x-axis, this is the y-axis, okay? I propose that sigma x is going to be sigma 2 plus sigma axial, okay? Let me digest that a little bit. So the stress that's going this way is whatever sigma 2 is, whatever the sigma due to the axial load is. Is everybody okay with that? So that's going to be, all right, that's going to be, what is that, 69.7 plus P over 5237.82 millimeters squared, right? Everybody okay with that? Sigma y is going to be sigma 1, which is 139.42, right? Actually, wait, I just realized something. This is why you don't go too far. That's going to be in newtons, right? Because if a kilonewton over a millimeter squared is a gigapascal, a newton over a millimeter squared is a megapascal. So whatever value of P that we get is going to be in newtons. Everybody okay with that? And then our tau xy is 1.3. Everybody okay with that? All right. Any questions? Bless you. Any questions? All right. So, does everybody have this so far? Actually, wait, I'm not going on to another panel. I'm just gonna do that. All right, so So let's see, we have sigma x is 69.7 plus sigma axial. We have sigma y is 139.42. We have tau xy is 1.3. Is everybody okay with that? Now remember, principal stresses, we have a sigma capital 1 and a sigma capital 2, right? So what is the formula for sigma capital 1? It's this right here, right? Here, let me... here are our formulas for our principal stresses, right? Y'all remember that? So remember, you have a state of stress, you're trying to rotate it to determine a worst case scenario. So which one is bigger? Do y'all remember? Which one do we traditionally take to be bigger, sigma 1 or sigma 2? Sigma 1, right? Because sigma 1 is this plus this quantity, sigma 2 is this minus that quantity, right? So our sigma 1 is sigma x plus sigma y over 2 plus that. So if you didn't like this problem, really the reason you didn't like this problem is algebra, okay? That's probably why. Okay, so what do we have here? We have, 69.7 plus sigma axial plus 139.42 over 2 plus, then over here, we have, 69.7 plus sigma axial minus 139.42 over 2 plus 1.3 squared. And that all has to equal what? What's our maximum allowable stress for this problem? What?
160 years. Yeah, 160
One-
megapascals.
160. So ultimately what we have to do is we have to solve for a sigma axial, right? Okay. Now, let's do a little bit of algebra, and then I actually want to show you something. It's really more for you mechanical engineers in the room. So 160 equals, now help me out over here, what's 69.7 plus 139.42? Okay, and then divide that by 2.
104.56.
Is everybody okay with that? Okay. And then over here, we have, let's see what we got here. What is sigma axial? Okay, so we have sigma axial. Okay, so what is 69.7 minus 139.42?
Minus 69.72.
Okay, and then what we'll do is we'll say that quantity squared, and then that's over 4 plus, and then this is, I think, 1.69. Did I do that right? Okay. Now there's a couple of ways of going about this problem. If the algebra scares you, we can get to this point right here and actually use goal seek, but we'll do that later. So let me but for now, just hold off. We'll hold off on that. Okay, so what can we do to simplify this? Well, what I'm going to do is get everything that's not a square root over to the left side of the equation. So we have 160 minus 104.56 minus sigma axial over 2 equals sigma axial minus 69.72 squared over 4 plus 1.69. Which, by the way, if you see me make like an algebra error, let me know, because I'm just sort of shooting at the hip at this point. Sound good? All right. So over here on the left, what can I do to simplify? What's 160 minus 104.56? What? 55.44 minus 1/2 sigma axial equals everybody okay with this? So what I can do is I can square this whole thing over here on the left and square this whole thing on the right. If I square everything on the right, everything, the square root cancels and I have sigma axial minus 69.72 squared over 4 plus 1.69. And then that equals what we have here on the right. We have 55.44 minus 1/2 sigma axial squared. Sound good? Break out a little bit of that foiling, right? Now we got to do some foiling. So first times first, so I'm going to need some help. What's 55.44 squared?
3,000.
What?
3,000. 3,073.
3,073.6. Minus, and then we'll have 2 times 1/2 times 55, so 55.44 sigma axial plus 1/4 sigma axial squared. Let me know, am I losing anybody? Let me know. Or is everybody okay with this? Everybody good? All right. And then over here on the right, let me move this down. Over here on the right, we have 1/4 times, okay, now we got to FOIL this. We got sigma axial squared minus, what's 2 times 69.72?
139.44.
Okay, plus, and 69.72 squared?
4860.9.
Right? So we'll distribute the 1/4 over here on the right, so 3073.6 minus 55.44 sigma axial plus 1/4 sigma axial squared equals 1/4 sigma axial squared minus, need some help there,
38.8 or 34.86.
and a little bit more help.
1215.2.
1215 point what?
2.
And then plus 1.69, right? Okay, so one of the things that we can do right now is we can cancel those, right? Then what we can do is we can start collecting like terms. So what I'm going to do is I'm going to add the 34.86 sigma axial to both sides, or to both sides to cancel it over here on the right. And then I am going to subtract the 3073.6 over here. So over here on the left, what is minus 55.44 plus 34.86?
Negative 20.58.
Negative 20.58 sigma axial equals, and then over here on the left, I've got that plus that minus that.
Mine is 1856.7.
So sigma axial equals what?
.22.
Do I have a second on that? And that's megapascals. Now remember that also equals, what was it? P over 5237. Right? So what's P? Say it again.
472,544.
And that's newtons, which is 472 kilograms. Now the book got 460. My guess is there's a rounding error in there somewhere, so don't quote me on the rounding. So it was algebra. There you go.
Thank you.
What do you think? Any questions? Now, I do want to show you, mechanical engineer, something because I think you need to see it. See this equation right here? All right, let me show you something. I don't think maybe you mechanical engineers use Excel now. Maybe you civils need to see it too. All right, so we're going to put a sigma axial term. What was the answer for sigma axial? Does anybody remember?
90.22.
90, okay? I'm just going to make a guess. Let's say it's 20. All right, what I'm going to do is this. I'm going to calculate what's on the right. So that divided by 2 plus 104.56 plus that, right? So think no, what was the answer? Say it again.
For P,
No, you're for sigma axial.
90.22.
So if I put in 90.22, what do I get? I get like 160. So, but let's say you didn't know that. So let's say you put 20. So what I can do is I can take the difference of that and whatever's on the left side of the equation, which is 160, right? So see this cell here? See what happens the closer I get to, watch this, 40, 50, 60, and then 90. See how it gets closer to 0? So what I can do is say, let's just put in a guess, and I can say data, where is it, what if analysis, goal seek, set that equal to 0 by changing whatever sigma axial is, and boom, there's the answer. Excel is awesome. If you're on a desert island and they ask you, like what you need, you don't need, like the whiteout from the Beatles or, a pocket knife or, a signal flare. You need Excel. Goal seek is awesome. That's all I'll say. Have you mechanicals done that before?
In your class?
No, I'm talking elsewhere.
No.
We teach you these tools for a reason. Seriously, it's a very valuable tool. I know you can't use it on an exam, but it'd have made your homework a lot easier. One other thing worth mentioning, the algebra on the exam is not that intense. I'll go ahead and tell you. That's Thursday. That's what I have on my calendar, Thursday at 8, right? Yes, no, 13. All right. We still got time. I want to address questions, because we did that one. That one's fine, but we still got plenty more time, so I don't want to restrict the entirety of the class to just this. I mean, there's a whole slew of other things we can talk about, so. The floor is yours. Please make wise use of the time. Don't be shy. I mean, I do get it. I know you're probably like, we're done, Dr. Mike. We're done.
We had a problem where there was some load and you needed to figure out the critical value of that load. So I didn't know if this was the right strategy, but just generally the strategy, it was like some trust thing.
Yeah.
So it was just a geometry problem, but you solve for whatever the forces in actual truss are. And then from those forces, you find out what P critical would be. Right?
Well, it's a little backwards. What I would do is you can figure out the P critical for each truss member without anything else going on, because all you need is the length of the member.
Right, yeah.
Once you get the length of the member and you recognize, since it's pen, K equals 1, you can solve for P critical right then and there. The question is, what value of W will cause you to reach P critical in each of those members? And so you can solve for that, and I'm making up numbers. But for one member, you're going to get 80 kips. And for the other member, you're going to get 50 kips.
Right.
And so which is the worst case scenario? It's the 50 kips. Because as you load and load and load, you're going to hit the 50 kips and fail the one column before you are the other.
So going to the statics part of it, you have to solve for the unknown load in two different ways, right? You have to solve for it in terms of one of the forces, and then solve for it in terms of the other force, and then use that to find what W critical would be, because you have to figure out which member is going to fail first. Right?
Well, yeah, but ignore the buckling. Ignore the buckling doesn't exist. But heck, be critical. Okay, you have a method of joints problem with a load on a joint, a W load on a joint. What's the force in each member?
Right.
Don't ignore that. You can do that with just basic statics. Now, once you get that, you're going to get, okay, if this is W, this might be 1.4 W, and this might be 1.2 W. And then look at each member independently and say, okay, let's take that. What W will cause P critical? Or did we just say the same thing? Okay. Yes.
For deflection of beams, can you go over how to use different boundary conditions? Like how to determine what your boundary conditions are going to be for different deflections?
Well, okay. The simplest way to do that is, there's a slide. Hold on. Here it is, right here. This is it in a nutshell. Okay, so if you ever have a boundary condition that looks like this or looks like this is y equals 0. Y equals 0. This is going to be y equals 0 and that equals 0. So, for the sake of discussion, let's say we have a problem that, I'm just making stuff up. Let's say this is the y-axis, this is the x-axis, and let's say there's a fixed end right here, okay? And the beam is L long. So our boundary conditions are at L, or at x equals L, theta equals 0, and at x equals L, y equals 0. And that's it, you know. If the fixed end was over here, it wouldn't be at x equals L, it'd be at x equals 0. Now, if instead of L, what if it's 20? At x equals 20, or at x equals 0. If you have a pinned end, it's just going to be, you're going to have x equals 0, and let's say x equals L, it's just going to be both y equals 0. And that's really it. Now, if I wanted to get, if if I wanted to be a big jerk, which I'm not going to be, instead of a hinge support or a pin support or a fixed support or something like that, I could put a spring on the end and say the deflection is K times X or something. But I'm not that mean. So on most days, I won't be that mean on Thursday. I don't think. I could throw some vibrations on it. What if I take the beam, do that to it? That should interest you, mechanical engineers.
We do that next class.
They say next semester, not now. But yeah, that's it. The big thing to recognize is when you're using double integration, how many boundary conditions do you need? I'm asking you, how many?
Two.
Two, there you go, yeah. Yeah, that, because, and the reason why is because where you're integrating twice, you're gonna have two constants of integration. So as long as you have two boundary conditions, you're good. And just so you're aware, and I'm not trying to go off on a tangent, but the determination of like constants of integration for boundary conditions is a problem that you're going to face as civil and mechanical engineers, and even the electrical engineers and whatnot face this problem throughout their career. I mean, if you have a heat transfer problem, you know, instead of, you know, deflection equals 0 and rotation equals 0, you've got a medium, right? You got some heat applied to it. You're going to say, well, the temperature here is 70 degrees. There's a boundary condition. And you're going to use that boundary condition to solve for arbitrary constants. It's kind of the same idea. Now, granted, just like in heat transfer, you know, just like in reinforced concrete design, we could usually get around all the calculus with a lot of closed form solutions for simple cases. But that's basically, in a nutshell, what we're doing. So, yeah. That is all. Mechanical and transfer. What a heat transfer. What's it talking about? Any other questions? I mean, come on, this is your time. I want you to feel relaxed and comfortable about the exam. So remember that age-old rule I said, when somebody asks a question, as soon as somebody asks it, what happens is just about half the class is like, yeah, I wanted to ask that question as well, but I didn't want to be the person asking it. So don't be shy.
When you have like some sort of member and it's getting some like load, you know, like some like press load put down and it's fixed at the bottom, and you're asking like, oh, what is the P critical here? You're always gonna use the weak axis moment of inertia, right? Because that's where it's going to.
For our purposes, yes, you're always going to use weak axis properties. And the only thing I will say about that is, and it doesn't affect you, but it affects the civil engineers in the room, when we take steel design, weak axis versus strong axis is going to be a thing. And how we address that is really going to be a major discussion point of that course. But for here, weak axis. So if you look up the properties of a W10 by 49, you don't use the I1, you use the I2. Again, it goes back to the yardstick. It's going to buckle the easy way, not the hard way.
And anything that on the file that we need as far as like moments of inertia or whatever, that'll all be.
The basic stuff, yes. Now that doesn't mean that I would just completely ignore. That doesn't mean I would completely ignore memorizing some basic ones. And it only helps you to just remember, oh, BH cubed over 12. I mean, if you don't just remember that offhand, it's not saying it, you know, putting it on your formula sheet's a bad idea, but all that's going to do is help you out. If you want to put that stuff on your formula sheet, that's fine, but please, goodness, don't waste half your formula sheet writing section properties, because I'm gonna give you, if there's any esoteric, I'm gonna give them to you, because, look, you're gonna be in a design office, you're gonna be on the FE exam, you're gonna have that stuff given to you anyways. I don't need you to memorize that, I don't see any value in it, yeah? You need to be able to use it, you don't need to memorize it. Y'all worried about the exam? You feeling relaxed about the exam? Is there anything about the exam that is worrying you? Y'all seem like you're ready for next week to be here, like nobody's business.
What time are you showing up tomorrow? How early can we take this, or not?
Tomorrow?
Next week.
My goodness. Well, what time do you want to start taking it? 6.
6 sounds good.
The looks that everybody else is giving you right now, they're like, you crazy?
I was one that said 6.
I'm saying everybody else.
All right, 6:30.
When do you all want to take the exam?
I can either 12 or 7.
Noon. I mean, they can.
Noon. That's not happening, man. I'll make you a deal, okay? I can be here in the building with the exams printed and ready to go at, I'm probably going to be here, early. And I'll come into the room at, let's say, 7:30. Like, I'll just come in and say, if I have everybody here, then we'll do it early. But I mean, if I'm not, yeah. But I don't think we're going to have, I'm just going to go ahead and tell you, I don't think every single person is going to be, if every single person is here at 7:30, we will start the exam at 7:30. But if there's one person missing, I'm waiting until the university scheduled time of 8 o'clock, because that's when the university says we're taking the exam. That's why I say if everybody's here, we'll do it early. But if there's even one person missing, we're not. And I don't think, I'm just going to be honest with you, I don't think everybody's going to be here at 7:30. You can arrange it, okay.
I can tell you right now. So, I got work.
So, looks like your plan just got shot.
I can make 7:45.
I'll take that. 7:45.
Maybe.
I have to ask, is there a reason for, is it like the Band-Aid methodology, just right off?
Extra time.
No, I didn't say that. I said we started early. I don't think this is going to be a time crunch exam, though.
You already get 2 hours. That's just one extra problem than a regular thing.
What he said.
Exactly. I need extra.
Oh my goodness. These students can be crafty sometimes. I will walk into the room at 7:45. If everybody's here, we'll start the exam. If not, I'm waiting till 8. Actually, I'll wait till everybody gets here. If everybody gets here, we'll start the exam early. But I'm not going to come in at 7:30 because I've already had a student say they're not going to be here.
And it's in this room.
It is in this room. Same bat time, same bat channel. Does anybody get that reference? Batman. Batman. Do you know the reference?
You talked to Michelin Man, right?
I say it's as bad as the Michelin Man. Ghostbusters. Why do they have Michelin Man on the race? Good. Have you watched the Ghostbusters since that discussion?
No, I have not.
Okay. You're already starting the exam with -20. Already. Now hold on. That race had a dinosaur in it. Next thing you know, you're going to tell me you haven't seen Jurassic Park.
I've seen Jurassic Park.
You haven't seen
I haven't
Jurassic
seen either.
I thought that was Godzilla.
Actually, it was Godzilla, but
And I have not seen it.
come
I
on.
haven't seen that.
Oh my goodness. The one that's really good, my wife is a huge Jurassic Park fan, so the one that's really going to be disappointed is my wife. I tell her I've got college students that haven't seen Jurassic Park, she's going to say, she's already said, she said, Stephanie's watching Jurassic Park. She's already said that. Any questions at all? All right, couple things. First off, good, 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 good. All right, you good? All right, so with that, a couple more things. Number one, housekeeping. I need your homework 8s here. If you haven't already turned it in, please do so. Course evals. Again, there's 4 of you that have yet to do them. I don't know about the CLO survey, but that'll turn on when everything closes. Again, you do your survey on your course outcomes. That's 10 free bonus homework points. So I leave that in your capable hands. The only other thing I will say is we will see each other on Thursday, and with that, this is like the 3rd or 4th time I've taught this class. I always have a blast teaching deformables. It's just, it's a really fundamental science. I mean, look, whether you're a civil engineer or a mechanical engineer, one of the things I said on day 1 is that when you get out of here and you go to a design firm or a manufacturing company or a DOH and you have to design a gear or a bridge or a whatever, this is the stuff that's going to be running through your head. You know, are the stresses lower than the allowable? Are the deflections within tolerance and whatnot? This is what you're gonna refer to. And I would argue that for, you know, engineers, you know, this course and maybe fluids and thermo, that's sort of the holy trinity of engineering. You know, if you're a mechanical, that is mechanical engineering, solids, fluids, and thermo. If you're a civil, well, we don't worry about thermo, but because we don't worry about thermo. But mechanics and fluids, these are very fundamental sciences, and so I hope that you have gotten some value out of the course. This is stuff that you're going to be using throughout your career. So I take it pretty seriously, making sure everybody's comfortable with the material. I hope you've had fun too in our 8 o'clock in the morning excursions into stresses and strains. It is really early, isn't it, for this stuff? I mean, this is like some of the most important stuff that you ever learn. There's a stand-up comedian named Lewis Black, and he starts talking about the economy, and he starts talking about different parameters about the economy. And he says, I know this about the economy because I took economics, and I'd explain it to you, but I flunked that course. Of course, it's not my fault. They taught it at 8 a.m. At what point I grabbed the professor and said, "Why are you teaching this stuff so early? You trying to keep it a secret or something?" There's absolutely nothing you can learn out of one bloodshot eye at 8 o'clock in the morning. I didn't set the schedule though. I didn't schedule it, so don't blame me for that. I would be here at 2 p.m. like everybody else. Then again, I had co-op at 2 p.m. All right, guys, that's all I had. It's been an absolute blast having you in class. We will see you Thursday at maybe 7:45. We'll see. That's all I got, guys.